To introduce myself, my name is Rowan. I'm a recent graduate of George Mason University. I got my PhD there, and my experience is in designing human-centered AR/VR interactions. More specifically, I like to design adaptive and context-aware AR/VR systems. So what do I mean about that? So if you think about interactions in general over time, you probably remember what browsing, I mean, maybe I'm aging myself here, but I remember browsing the web in 1997, and this is what it looks like. Interfaces were static, they were not personalized in any way. There's no contextual awareness of the user themselves or whatever their environment is. Now, if you fast forward to browsing the web today, the web is more personalized. It's more context aware. There's a lot going on under the hood because there's lots of contextual awareness of the user and their environment, and that's due to machine learning models that are going on under the hood. And so the web browsing the web right now is quite a bit adaptive compared to what it was in 1997. So how I view AR/VR interactions, they're not quite as static as browsing the web of yesteryear, but we're not there to the contextual awareness and adaptiveness of browsing the web today. So here's a very cool art project. It's called Hyperreality. It's a dystopic visualization or look into how mixed reality could look like in the future. And if you notice looking at this project, me as a researcher, my researcher brain identified a few problems, and it's not solely because there's just too much going on in the screen. Sure, that's one problem, but there are various problems that you can identify. So if you notice the advertisements that are placed in this bus, there's just, first of all, too many of them, and they're just not well integrated within the environment, i.e. there's no awareness of the user's behavior or the environment itself. It's not integrated in a place that attracts the user. It's just haphazardly placed along this environment. And one more thing, the most important message right here, watch your step, as the user is exiting the bus, is probably being ignored because it is being placed at the wrong place. Again, no environment or behavior of the user is being integrated. Again, one other example, you see two arrows that are pointing to the pharmacy. So the user, if you watch this video, you'll see that the user is intending to go to the grocery shop. So why are we showing arrows that are pointing to a pharmacy? Sure, they might be advertisements, and in that case, why are we showing two arrows? Why can't we pick the most attractive arrow that is well integrated into the environment and add that into this screen? Again, no behavior or environmental awareness is integrated into these systems. So in my work in general, I use the computational HCI framework to sort of embed contextual awareness into AR/VR systems. What is computational interaction? It's essentially applying computational thinking, abstraction, automation, analysis to enhance the interaction between users and systems. Here's a little graphic of how these, at least my framework works, or the framework that I'm working in is graphed. So assuming you have a user and a system, we can represent this system with a mathematical function, i.e. we can have an optimization or a machine learning algorithm that sort of drives the interaction between the user and the system. And we can also extract information or the context of the user, i.e. their behavior or from their environment, and put it into that mathematical model and adapt that interaction between the user and the system. So there are various challenges in designing these mixed reality systems or these interactions, but because these challenges are mostly related to the dynamic and 3D nature of AR. I would say they're more of opportunities to enhance interactions in general. So, again, going back to browsing 2D interfaces, the user is going from one web page to another, one 2D page to another, whereas augmented reality is three-dimensional. The user can move from one place to another, so content needs to be integrated well into the environment. So in that sense, you need a lot of semantic understanding of the environment, geometric understanding of the environment to integrate content into these mixed reality experiences. Now, if even at the state that AR is today, most users currently use mobile displays to interact with augmented reality in general. So that presents additional challenges. So how do we integrate these interfaces where the user has a limited field of view? Also, it's less natural to interact with a mobile device compared to gesture interactions. So us as researchers, we have to figure out the best ways to interact with this content from a 2D display. And the content is by nature three-dimensional because it is placed in 3D. Even if we're talking about glasses displays or HMDs, and the user's field of view is much less limited than mobile displays, we still have to consider where to place content again, how to integrate it well into the environment without breaking the best feature of mixed reality or VR, the immersiveness of these experiences. Also, hybrid displays. I don't foresee a future where we get rid of typing or writing on pads. So in that sense, we have to figure out if we are moving towards these mixed reality experiences, we have to integrate 2D surfaces where it gives you the precision of writing or drawing into these augmented reality experiences where you're using gesture control to interact with the environment. So there are challenges into how do we find a medium, happy medium between these two interactions. Most of my work has been in using user behavior and using behavioral analysis, i.e. tracking, to facilitate these interactions in mixed reality or augmented reality. Now, I've looked into a lot of research in eye tracking, and if you look into the research in eye tracking, it's usually the researchers are usually studying 2D displays. And once you take their mathematical models and implement it into VR, you have to consider the 3D nature of these environments, and the user's behavior changes once you put them in a three-dimensional environment. So you have to consider that in developing this mathematical model that drives the interaction. Also, in AR, VR, there are novel modes of interaction. There is gesture recognition as you know it, and there's also gaze-based interaction, which is becoming pretty popular when it comes to interacting with content, especially for folks who are not fully bodied or disabled. There's also a lot of work in integrating both gesture-based and gesture-based, gaze-based and gesture-based interactions together to work in one full system, and there are challenges within that as well. So I'll go through my work, and essentially it scratches the surface to making AR, VR more usable and context-aware of the user. So I'll start off by talking about my adaptive gaze-based navigation aid, and then we'll talk about my work in optimizing the placement of elements or objects in a virtual environment, and that uses both behavioral and environmental awareness of the user. And then finally, I'll talk about my AR drawing application, which essentially embodies, geometric understanding of the environment to place VR content. So starting with our adaptive navigation aid. So I attempt to solve these problems, with this specific project, I attempt to solve the problem of creating a navigation aid that is adaptive using user's gaze. So if you've ever seen navigation aids, if you played video games, you know that there are several types, but we've identified a couple. One type is navigation maps, mini-maps, where you're shown where you are in the environment, and then you're directed within that mini-map to where you should go. One type of navigation aid is arrows, where you're just shown an arrow at the top of the screen, and you follow that arrow to get to your destination. Now, if you think about these aids, in video games, regular video games, they work pretty fine because you are still watching or playing this content at a 2D screen. But take that into VR, it breaks the immersiveness of VR because you have an arrow that's somewhat like blocking your screen all the time. So how do we make these aids more immersive? So why don't we just adaptively show these aids as the user needs it? So we actually found out that we can. So if we use an HMD with eye tracking capabilities, we can track users' gaze from this headset, and using the gaze patterns, we can input these patterns into a machine learning classifier, and this classifier will tell us when the user needs navigation help. So if a user is navigating in a VR environment, we can just extract their gaze patterns and put it into this classifier, and the classifier will tell us whether the user's needing help at this moment. If they don't need help, then we don't show this aid. If they do, then we just show the aid. So it's essentially an adaptive sort of experience. So in order to get this navigation aid to work, we started off by collecting data that will help us train this machine learning classifier. So we had to conduct an experiment to collect this data. And in this experiment, users are dropped at this starting flag, and they are asked to follow this embedded path to a fruit in this specific environment. So once they get to the fruit, we disable this embedded path, and users can manually trigger these embedded paths. And in that point of the experiment, we ask users to get back to the starting point. And to add a little bit of confusion, because I don't know if you've tried training machine learning models, you need a lot of positive examples, you need a lot of points where the user is feeling confused. We blocked users' paths that they've initially taken to get to this fruit. That way we confuse them more, they press the trigger more. And so once the experiment ends, once the user gets to the starting flag. So this is the little map of the environment that we've used. The starting flags are shown right here, where the stars are, and the fruit are shown right there. So if you notice this environment, it's quite maze-like and confusing. And that is by design, because we needed as many positive points, as many points of confusion for the user. That way they trigger this navigation aid and give us more examples for the machine learning model. Here's a little walkthrough of this environment that we've designed. And again, the buildings all look the same. And it is by design. We did not want users to easily navigate this environment because we needed more positive points to train this classifier. So, all right, cool. We collected this data. We trained a classifier that is able to classify using users' gaze patterns or where they're looking when they're feeling lost in a navigation experience. We wanted to validate whether, our model works, whether this is actually a valid, application of navigation. So we took the same mini-map, we colored it so that we give users more opportunities or ability to navigate it easier. They have neighborhoods now, so they can know where they are within the environment. We also place in the center of the environment because a little tower, because landmarks are shown in studies to be, the key feature to navigating for humans. So in this particular user study, users completed this same task in 3 ways. First of all, they navigated using an adaptive and permanent version of this arrow, and an adaptive and permanent map, and then they, as a control, navigation aid. So here's a sample of the user navigating using this adaptive aid. You can see that they hit a barrier right there, and then the aid shows up on the top to guide them to where they should be going. And here's what we found. So here is a plot of users' gaze on the screen using the permanent map and the adaptive arrow, the permanent arrow and adaptive arrow. And if you just observe this data, you can see that using the permanent arrow, the users are just focusing on the horizon and on this arrow. And when it comes to the adaptive arrow, you can see that there's more spread of data points or of where the user's looking, and it's more spread out throughout the environment. So this tells us that users are actually exploring the environment, but at the same time, we measured the time that it takes them to get from point A to B, and it's quite efficient. It's the same efficiency as having a permanent map or a permanent arrow. So in conclusion, having an adaptive arrow in this sort of model gives us a more immersive experience. At the same time, it doesn't sacrifice the efficiency of users. Now, we took that same approach and we plotted out the mini-maps. When it comes to the permanent and adaptive mini-maps, there's no difference between the immersiveness of the experience. Why is that? Well, we found out by looking at the data that users essentially are confused while navigating using mini-maps. They would look at the mini-map, stop, and then go to where they want to go, and then stop again. So it's a lot more confusing than using an arrow. So I think that's why this is happening. So as you have probably heard, machine learning models tend to not generalize well. What do I mean about that? We created a new experience, a more rural navigation experience, a VR village, and this is the scene that we used. And so we asked users to complete the same study, but using this sort of scene, a more rural scene. And so we took users' data and we analyzed it, and we put it into the machine learning model to determine whether it's as accurate as navigating the city. Our accuracy dropped to 80%. Now, why is that? Here's user's gaze navigating a city versus a village. You can see that in the village, people's gaze is a little more spread out. It's a little more spherical, whereas in the city, you can see like a U-shaped pattern, meaning users are looking at the city blocks in order to navigate. So this tells us that in order to train a machine learning model to determine or to help users navigate, you have to look at different navigation experiences and sort of train a generalized machine learning model based on these variety of experiences. So this particular paper, we wanted to explore a virtual environment design. What do I mean about that? So in this project, we wanted to explore the optimizing the placement of 2D elements, something like advertisements in an environment or artwork in a virtual museum. And all of this is based on visual attention analysis. So what I mean about that is we have an eye tracking data set and we put it into an attention classifier. So what this attention classifier tells us is, okay, given this placement of an element in that specific spot, and these are the features of this element, how much attention is it going to get being placed in X spot? So once we have that classifier trained on this gaze data, we put it into an optimization. So given an empty input scene, this optimization can place elements for you in that scene such that they meet a specific goal of attention, such that the elements are not in your scene in its entirety reaches its set amount of attention. And So for this specific project, we designed 2 virtual environments. One is based on the Kenmore subway station in Boston. I don't know if you guys have been to Boston. And the other is based on MoMA in New York City. So we designed these 2 environments, and we allowed users to navigate these environments. And we collected their eye tracking data. So these users are placed in this environment. They look around this environment, and we randomly place a set of elements in these environments. And so we essentially record the amount of time they take to look at each environment in seconds, at each element in seconds. Once we record that, we have determined which elements have received as X amount of attention. So with the help of some museum curators and designers, we engineered a set of features that gave us an accurate classifier, meaning you give this classifier features like the height and width, you give it the distance from the floor, you give it distance from light sources, distance from common paths that users could take, and distance from entrances, and an occlusion metrics that tells us how much this element is occluded, or it's harder or easier to see, and distance from the center of the screen. And so essentially this classifier, given these set of features, can tell us this placement will give us, with this height, width, distance from these light sources, will tell us, okay, this will receive 10 seconds of attention. So we know that from this classifier. And so given that sort of classifier, we put it in an optimization. And so this is a demo of this optimization, and it's automatically placing these paintings in this museum according to the predicted amount of attention they could receive. You can see that this color indicates the amount of attention it receives, and it converges once it reaches the user's pre-specified goal. The user would say, hey, I want in totality 10 seconds of attention for all these paintings, and then it would automatically place it for them. We did a couple of experiments with that. So the user can specify the number of elements that they could place in this virtual museum or virtual environment. These 2 examples all have the same amount of attention given from the machine learning model, but they have different number of elements that are placed in this environment. Users can also constrain the visual elements in a spot. So if a designer intends to, hey, I want to place these 3 blue paintings at that specific spot and constrain them for me, the optimization will work with that constraint and place other elements such that it meets the designer's goal of attention. One experiment is, okay, let's say there's a scenario where the level designer or the game designer is contracted to run 2 advertisement campaign for 2 competitors. Let's say it's McDonald's and Burger King. In the spirit of fairness, let's say McDonald's and Burger King are all paying the same amount for their campaigns. So the designer has to give both of these competitors the same amount of attention. So in this case, both the elements that are in black and purple have received the same amount of attention. And at the same time, the optimization can work concurrently to place place elements such that they reach a different amount of attention. So let's say McDonald's pays more for their campaign. In this case, we give them 21,000 milliseconds, whereas we give Burger King 9,000 milliseconds. Okay, so based on that, given the success of that framework, we thought about how do we place, okay, we've worked on paintings and 2D elements. Beyond that, there are some challenges to placing things that are more three-dimensional, like products in a virtual store. So we wanted to tackle that problem. So in that specific problem, we're not working with 2D elements. There are also a lot of design constraints that are more specific towards the placement of products in a store that are not present in 2D elements. What do I mean about that? So if you've ever been to a store, hopefully stuff is being placed at an equal distance. Things are not cluttered in one spot versus another. One thing is there's a concept in storefront design where elements that are larger are being placed on the bottom shelves, whereas elements that are smaller are being placed at the top. So we had to integrate that constraint as well. In addition to that, crowdedness. Elements should not be crowded at a specific spot in this virtual store. So all of these are constraints that have been added in addition to the visual attention constraint that we specified. So essentially our machine learning model now considers these constraints in addition to the constraint of amount of visual attention that these elements could receive. So we ran the same framework with placing products in a store, and these are examples of stores that we've come up with. Here's a toy store. All of these have been generated by our optimization. Now, finally, I worked on this project during my internship with Adobe. And in this specific project, we wanted to explore the problem of in situ environment-aware 3D curves in mobile AR. What do I mean about that? If you ever tried drawing using a mobile device, you've seen several modes of drawing in a mobile device. One of them is mid-air drawing. You take whatever the user's swipes are or gestures on this mobile device, and you place these strokes to where the device is. Now, this is a very intuitive method, and I'm sure anybody can pick it up. But it does suffer from precision issues, meaning the user is probably not aware of where they're exactly placing this stroke. So that's one major issue with this specific drawing modality. One other drawing modality that it's been explored in research, not so much in commercial projects, but drawing on proxies. So in that specific drawing experience, the user would place a proxy or a plane, a square in the environment, and they would sketch out their strokes within that specific plane, and they would be automatically restricted to this plane. Now, this is very accurate because your strokes are restricted within this 3-dimensional or 2-dimensional body, but again, it's not as intuitive. Any 9-year-old would probably not pick this up as easily as mid-air drawing. So the geometric proxies that I mentioned earlier, these 2D planes, are essentially 2-dimensional. So if you think about drawing on a 2D plane, you're restricted within that 2D plane. So creating strokes like this, where these strokes interact with the environment and its 3-dimensional nature, is not possible. These are demos from our project. So let's say the user wants to draw a curve in an inaccessible location. Let's say you have a Christmas tree and you want to place lights around it. Unless you have a jetpack handy, you won't be able to reach the top of the tree. So mid-air drawing is almost impossible, or actually impossible. And proxies are first of all 2-dimensional, and in the same time, you have to place them manually, so it's unlikely that you'll be able to reach the top of the tree. One additional problem is 2D devices or mobile devices have a limited field of view. So when you're drawing strokes in augmented reality, you're restricted to that field of view. Your strokes are restricted to that field of view. So you won't be able to create this sort of curve using these two methods. Moreover, users who are not able-bodied or have limited mobility, it might not be easy for them if they were going to create a plane path or animation plane path for a plane flying around a room. They won't be able to do it as easily using mid-air drawing or drawing on these proxies. So there must be a way for us to integrate multi-view drawing of curves. So in this project, we created a tool that allows users to scan the environment geometry. And using this scan, the user can draw strokes, and they can also place three-dimensional proxies. And these strokes, or this entire curve, is interpolated such that it interacts with the geometry of the environment as well as the geometry that the user plays. And also these strokes, why are these strokes so important, is because they enable content creators to design animations like this, for example. So finally, I'll briefly summarize my other work in computational interaction. So I've worked on another project with Adobe, and it was mostly tied to character design. So in this specific project, we designed a tool that helps character designers automatically color their characters. So you can see that the user is sketching the character, and it's automatically being colored using a GAN. And the user can just pick the style that they want, and it's automatically generated for them. Why is this helpful? Well, in character design, designers typically go through a process where they design this low-res thumbnail of the character, and that tends to be tedious, recoloring that same art piece over and over again with their director until they're happy with it. So this sort of facilitates and speeds up the process before they start and create and design the entirety of their character. So it serves as a visualization tool, essentially. One other project is we designed a virtual pet trained with real pet behavioral data for a mixed reality. So this data essentially was created by tracking a cat in an apartment. And we used this behavioral data of this cat to train another machine learning model that essentially gives us the sequence of behavior that this cat should exhibit if it was realistic. So given this data, the cat behaves in the environment in a correct sequence based on this behavioral data. This cat also understands what's going on in the environment. It knows what a table is. It knows where its scratcher is. It scratches from its scratcher, and it knows how to eat, where to eat from. It eats from a bowl and not on a table. So we've embedded environmental awareness in that cat. It also would know where to walk. For example, if the path for the cat is too narrow, it would not choose to go through that path, for example. So I am very interested in using mixed reality for accessibility. And this specific paper, I helped develop a mixed reality AAC tool. And in this AAC tool, it helps users communicate in grocery shopping scenarios. So it would detect objects that are present in the scene, and then it would suggest messages for the users to just click through. Typically how it's done is the user would go through a whole big menu of things that they would have to click through in order to communicate via voice. But in this case, we essentially automate the process by suggesting the more reasonable messages based on what's there, what's present in the scene. I'm also interested in training in mixed reality, and by that we also I also helped my advisor design and create a workshop on 3D content creation for simulate training in mixed reality. And there's a lot of interest in that specific domain. So we thought about, okay, how do we facilitate this for researchers? So we went ahead and created a survey where we compiled all the work that we know of when it comes to mixed reality training and using mixed reality tools for training. So that paper covers that. If you're interested in that, please check it out. So what's next? What problems am I interested in working on, and what problems are essentially the gap for us to get to these context-aware mixed reality interactions? So first of all, let me preface this by saying the issue with getting these context-aware interactions or getting mixed reality to the mainstream is not only a research problem. There's a lot of infrastructure issues that need to be fixed to get mixed reality to the mainstream. One thing you probably heard researchers talk about is 5G technology. We do need a lot of infrastructure to process geometry in the scene, process all this information, and render this information accurately to the user. So that's part of it. Another part of it is how do we automatically integrate content into the scene? Typically, how content is integrated into a scene is the designer would typically manually place content. So if you were to design a working application, you would have to place this content manually. Now that's kind of problematic in the sense that in this specific project or this research paper, the user specifies the placement of these 2D screens in their work environment. So the user would place them once. And so if they move to a different spot, the AR app would automatically detect their scene and the organization of the scene and would place elements according to that. Now, this is not manual, but still not totally automatic. So the user still has to do that manual work of figuring out where to place the content such that it makes sense. So if you remembered, one of my papers is about placing 2D elements in a scene. So why can't we integrate these approaches into mixed reality as well, such that we just don't only consider attention, we could consider other things like visibility of elements, the ability to interact with these elements, which ones are closest to us, which ones give us the ability to interact with these elements in a specific way, in addition to attention. Attention is still important if you want to display important messages to the user. Also, to make this a little more complicated, things are much more difficult to automate when you're thinking or considering multiple users who are interacting with that specific content. So that adds a layer of complexity. One thing that I'm also interested in is interactive storytelling via spatial AR. If you've experienced the pandemics and you've been exhausted by Zoom, I feel like we can make this experience much better if we integrate spatial AR into it. What do I mean about that? This is the late Hans Rosling that he's displaying or talking about a data visualization. And you can see that he's interacting with this data. He's touching it. He's telling you as he's touching it, the data is moving and giving you animations. And that's what's great about interactive or spatial AR. It gives you much more control and it's much more interesting and for the user. Of course, researchers have explored this before. In this specific paper, you associate users' gestures with these elements in the scene. The user still has to do manual work to associate these gestures with the movement of elements, but it's still somewhere. I wanted to get to a place where you can have presentations or interactive experiences where designers can easily create these experiences and you can interact with elements in your room such that it's more of an engaging process. So one addition to that is because we're working with in mobile environments, users could also interact with these elements as well. Users, if it is in a, for example, classroom environment, the students can touch the data to get more information. The users can engage with the data in different ways. So it makes it a better learning experience and better presentation experience in general. So I think this is where AR shines, essentially. So to summarize, I spoke about my adaptive navigation aid for navigating in VR. I also talked about the automation of placing placement of elements in VR, and finally, mobile AR curve placement. I'd like to thank my collaborators for all their support. I couldn't have gotten here without them. My collaborators at George Mason and my advisor, and of course my collaborators at Adobe and Meta. Finally, I'd like to thank you all and the organizers at MAGFest for inviting me. I'm super happy to be here. I'd love to take your questions as well. Thank you all for coming. And here's my QR code if you want to check out my website or find my email to contact me. It'd be perfect.
I have a question.
Go ahead.
Concerning the museum scenario, is context aware content optimization? So you consider the content of the
That's
especially for human or animal things.
Yes, that's the perfect question. So we actually thought about that during the design of this algorithm. So in that specific, in the data collection and both the experiments, the contents of the paintings was randomly generated and shuffled so that users don't associate specific paintings with a specific spot, meaning an attractive painting is never going to be placed at the same spot.
Related to that.
Yeah.
I'm at a museum. I pay attention to the page of my life. But occasionally I stop and look at God, that's awful. Did you get an anthem of that?
No. No. So in that specific, we actually, not to shame any of the artists we used, but we used bland-looking landmark paintings as much as possible. And in addition to that, like every session, it's randomized, whatever the content is. And we didn't find any patterns when it comes to the content versus the painting placement. One work by Professor Yu, I'm not sure if it's published yet, but he considers the content of the paintings and how it influences the users in the environment. Yeah.
That would be a good study regarding advertising content.
Yeah, I mean it's actually well studied. The content itself, there's a lot of work when it comes to what attracts attention in paintings and that sort of stuff. Yeah. Go ahead.
Early on, you had mentioned that you removed all landmarks and purposely made the city as difficult and that's possible so that it's as positive data as possible. So do you expect moderate to large scale changes in the algorithm or optimization if you would attempt to use that in a modern basis?
So that's a good question, but here's the thing. A lot of these eye tracking experiments that are currently being done in VR are quite controlled. So that's why you don't see a lot of augmented reality or mixed reality eye tracking experiments, because it's really hard to control these environments, whereas in VR you can actually have control of what the user's looking at. You can restrict users' gaze to look at the navigation experience, although it's kind of difficult even in that case, as opposed to looking at, oh, this person is walking by me, or there's X distraction. So that's a good question, yeah.
I made that because if you take out all the other people that didn't see practically how a user behaves in that kind of positive data-rich environment in an actual city. I imagine the difference in how that kind of functions will materially affect how you create the top level.
Yeah, so if you take the user, the same users in a real space or real navigation environment, their gaze behavior is going to change because there's a lot of external factors that influence their gaze as compared to our environment. Even in our environment, we took it from a city to a rural one, and the accuracy dropped. So it tells us that these sort of algorithms, I mean, they're much more difficult to generalize than we think. Yeah. Go ahead.
So I'd also like to add that a lot of AR devices are usually mobile.
Yes. Mm-hmm.
And it will be like a lot harder to do like eye tracking tests for them because, like, for example, you can look the other way while the AR device.
Mm-hmm.
And in virtual reality, you're basically directly like looking at it.
That's a good, yeah, I agree. I think like that sort of goes back into the original thinking of eye tracking studies. If you've ever looked at eye tracking studies of the past prior to VR, you'll see that it's a very controlled environment. There's a screen right in front of the user. The user can't move. The user has to stay in that specific spot, and there's just cameras tracking what the user does. And I think adding a mobile device where the mobile device moves and sometimes the user's eyes are occluded might make it a little difficult. I think the usage of these sort of eye tracking apps will shine probably in HMDs that have eye tracking capability.
This would also like work better if AR glasses are more available, but then they generally develop.
I think so too.
It's not for like common use.
Yeah, not now. I don't think they're for common use at the moment, but they are working on getting them to common use because I don't know. I think they're quite integral. I mean, I can talk a little bit about my meta project. In that specific project, we used eye tracking to figure out if there are any things happening with the system that the users made mistakes. So using their eye gaze patterns, we can detect, oh, the user's feeling uncomfortable now. We show them a different UI instead of, using gesture-based recognition or using any other modality to detect it. So it's definitely something that's going to be integrated. I don't know how how or when it will be integrated because, again, it's not widely available. It's sort of. It also doesn't work with everybody. Like us wearing glasses can't, interact with eye tracking devices. Some people of color can't interact with eye tracking devices. So it's not as widely, usable as we hope. Yeah, go ahead.
I think really good presentation. I think you explained things very well, like the context awareness. Mm-hmm. So you explained like the what and how really well. So why do you research it? Why do you think it's important to research even forward?
So I think so there are a lot of bottlenecks to getting mixed reality devices to the mainstream. One of them is this. It's a rich environment, but we have not figured out ways to allow us to integrate content into the environment. And I think it's a more difficult problem than 2D screens, because 2D screens, all we had to do was figure out the layout of elements within this 2D screen. Whereas here, we have a three-dimensional space, and we have more interactive modalities. We have gesture, we have gaze, we have, where the user is relative to this content. So that's why I think it's important, and it will be impactful, especially when it comes to working via mixed reality, which I think is going to be a thing. Yeah.
Really nice. What was the study that you used?
Mm-hmm.
What were the corporate demographics? Were they what was the gender ratio? How were their racial makeups?
I don't remember the exact numbers, but it was pretty split. There was no, overwhelming gender in that study. I don't remember if we collected the racial makeup of our participants, but in general, I think these are, the initial point to where we should get mixed reality studies. I don't think this is, the best usability study in the universe, but it's a point that for us to validate these sort of systems.
Yeah, because have you done any training on any specific gender stratified training data or anything like that? Reality a little different depending on their social and cultural backgrounds. So kind of personality is a little bit more towards
Yeah, I agree. I think that's a good way to think of it, but I don't know. I personally, my research direction is not in that, because I don't think I'm a sociologist or qualified to answer these questions. I am more of a system builder and then validator. I hope that one day when we do integrate these sort of systems, that we'll have more extensive studies into how to, adapt these systems according to the variety of people that we could have using these systems. Yeah.
Related to that question, how many thousands of people do you
25 to 30, depending on the study. Yeah.
I'm just curious how you got numbers.
Yeah, how did I come up with that?
525 people.
So we try to get as many people as possible. Of course, I mean, it's in a university settings, it's not easy getting participants. In the Meta one, I think I've gotten more, but still, it's not enough.
Meta one obviously used the prototype from Meta.
Yeah.
In the university setting, which hardware do you use?
For both the eye tracking ones, this was done before the Vive Pro Eye, so I did not have the privilege of using the Vive Pro Eye. I used Fove. I don't know if you guys remember that startup. It was quite excruciating, but we got it to work. The API was difficult, but it gave us something. But I recommend, if you were to do eye tracking studies, Vive Pro Eyes is the way to go. So I used the Fove. Go ahead.
A bit of a more concrete question. For an app developer that wants to show a high user interface elements, based on what you've done, where do you rate behavior classification, searching for an element, versus the user dwelling on the portion of the visual field where that element would appear, versus requesting it specifically with a button press or something?
That's a good question. So what we did is we let the machine learning model take care of all of that. All we did is we gave the machine learning model, hey, the user's looking here, and then they're looking there, and you figure out how long the user is dwelling and what makes sense. So essentially, we gave it a sequence of gaze patterns in a sequence of time. And then it found out what makes sense when it comes to classifying this. But that's actually, in most extensive eye tracking studies, you would have different features, like how much the user would dwell on something, how frequently the user changes their gaze. But in our case, we just used a machine learning model, and it spit out the right, results. Yep.
Please go to the topic about that.
So you mentioned you're interested in in systems, right?
Yep.
So there's a spectrum of how users like to have things show to them, or want to set the preferences, or if they want the preferences to be set by them. So how do you think such a system will look like in the future? Because sometimes collecting user data generates profit to a third party, but then for a first party user data.
Yeah, I mean that's a philosophical question with all machine learning models, even the machine learning models that we have right now. I am an HCI researcher, so I am for human-in-the-loop sort of systems. I don't know how corporations are going to handle it, but what I hope is human-in-the-loop is the way to go. Yeah. Go ahead.
So, with regard to the data that you when you're running these experiments, do you take into account like, the subject's emotional state or issues like if I'm doing work at the end of the day that's taking 5 hours and what type of work I need to press
Yeah, that's actually a perfect question. And so that is a good question. Why? Because, I mean, when we collected this data, it just gave us a set of like gaze points or gaze patterns or gaze sequences. The user's looking up, looking at this specific spot, and then a set of times when the user pressed the button. Now, pressing the button doesn't necessarily indicate that the user wants navigation help. The user could just be lazy and they want to get there as soon as possible. They want to finish this experiment. So it's not necessarily the best way. So what we did is we essentially manually chose a window where we think, okay, this window is going to be when the user is feeling lost. But a more accurate and careful method in labeling this data or figuring out where exactly the user felt lost is I probably would use EEG data to determine when they are more exhibiting these behaviors of they're feeling confused and lost, as opposed to us guessing that, oh, in this window we think that they're feeling lost. Yeah. Any other questions?
I'd just like to add that some of these questions boil down to statistics.
Yeah, but understand, she's not interested in the data, but she wants to get prove that this is a
Yep.
viable tool and it doesn't.
But
Yeah.
good experiment design is the same.
I think you're absolutely right. Good systems require extensive usability tests. I am not a usability expert, but hopefully other researchers will take my work and scrutinize it from a usability standpoint, and that's what I'm hoping. I don't think my work is the all and be all. Yeah. Go ahead.
So I feel about this from what I've heard over the last few months. Machine learning models with very large numbers of parameters actually function very well to computationally expect. Do you see that as a barrier to doing some of the research that maybe, or at least getting further into where a much larger data sample and more parameters might be necessary to run
I don't think it's necessarily a hindrance. The more accurate machine learning model, the better. And I mean, as far as I know, all the machine learning models that I've used are quite simple, and they still reach a 90% accuracy and above. So you don't, you can do a proof of concept without needing a huge machine learning model and a huge data set. But if that navigation aid experiment were to be generalized, I expect whoever is designing that system to collect an extensive amount of data from a whole lot of environments than just two. Yep, go ahead.
So, I think when she was talking about, like, you have a mobile device and you're, like, looking around at the device. So, like, when you're exploring a city or a village, right? What I usually do is, like, if I'm walking away, I know where I'm going, but I'm just looking around, just observing the things. So I'm wondering if there any usage of the, like, direction and path position within, like, any research that you did?
Yeah, so in this project, so we use the user's gaze relative to their head. So the angle between the head and the gaze, and that gave us the sequence of the user, the accurate sequence to determine where the user's looking. There are multiple metrics that you could use. One of them is fixation, the amount of time that the user could fixate on an object. In our case, that didn't work so well. The best thing that worked for us was using the angle and the changes in angle. Yeah.
You're amazed that some of the new devices coming out are not going to be able to detect eye picture, eye brightness,
Yep, pupil, yeah.
the muscles around the eye.
Yeah.
It'll all be more data for the machine learning
Yeah, exactly.
along with that. So it's going to be very interesting.
Yeah. Any other questions? Yep, go ahead.
Uptake of some of this technology, particularly in that initial section at the start where they showed us you going to a store and getting data about people like this product, this manufacturing stuff. My first thought was, you're going to need, all of that data in one place and all of that data sent to your device, which is, it seems like a larger burden on companies.
It's as large of a burden as, that Netflix has for collecting data, I think. Now, because, again, going back to that specific project, we did not, record any complicated data. We only recorded the amount of time that they're looking at specific things. And we used the simple geometric features of these things and their specific placement to train the model. You can dump a lot more data and it'll get more accurate. But I don't think it's a hindrance as much as you think. I think it's more of an advantage, though not for us because our data is being collected, but for these machine learning algorithms. All right, I think, thank you all for coming. I appreciated the discussion. This is so insightful.